Good evening, everyone. It's my pleasure to welcome you all to the session, Decoding Microcontroller from Architecture to Execution, hosted by IEEE SCCS Kerala chapter. Today, we have the privilege of being joined by our esteemed guest speaker, Mr. 𝗬𝗂𝗧𝗂𝗧𝗧, Embedded Systems Specialist and Senior System Software Engineer at TESSOLVE. Without further delay, I would like to invite 𝗬𝗂𝗧𝗧 sir to take over the virtual platform and share his valuable insights on microcontrollers covering architecture, memory mapping, and code execution. Let's give him a warm welcome and get started with this session. Over to you, sir.
Thank you, Niranjana. So I'm taking over the platform. Um, Let me present my screen. So we are starting. The intention of this discussion is to understand, as the host said, we are going to understand a microcontroller in deep. So decoding microcontroller architecture to execution, and discover how microcontroller operates from core to peripheral interaction. So the first microcontroller was invented by Texas Instruments. Now, so many companies are manufacturing it for different purposes, like automotive, industrial, communication. So many areas are owned by microcontrollers now in electronics industry. So this session actually aims to deep dive into microcontroller architecture, how the microcontroller is architectured internally, what are its components, and how software can be developed for microcontroller application, how microcontroller application can be developed, what are the tools associated with it, what are the procedure, how a code executes inside the microcontroller. These are the main agenda of today's discussion. Let's go to agenda. So this is the agenda. First, we will ask the general question, what is a microcontroller? Then classification of microcontroller based on ISA, ARM and RISC-free architecture, internal connectivity, how peripherals talk to CPU, microcontroller booting process, understanding the memory map, behind the scenes of code compilation. Then next, at the last Q&A, question and answers, then open discussion. You might feel this as a hailstorm or rain with the hailstorms. So like bombardment of information. So many things we will be discussing. It might, you may feel like you are not able to understand the concepts, but I will try to help you at the best to understand the concept. If you have any doubts, you can put it in the chat, or in between somewhere I will stop. That time you can ask the question. Okay, so let me continue to the next slide. So what is microcontroller? Actually, it's a compact integrated chip controlling devices through programmed digital instruction. So we have to have a computer where we have some development tools available, like software. Generally, we call it as compiler. With the help of compiler, we will develop some code. Why we need compiler? Why we need computer? That you will get to know by going through the next slides. Okay, so a microcontroller is a combination of everything, like ADC, clock, RAM, CPU, ROM, input-output devices, DAC. So a microcontroller is an integrated circuit which consists of so many other integrated circuits. So a combination of integrated circuit with other integrated circuits. So we need a particular device called programmer. This one, Keil Tools by Udemy. There are so many other similar products available in the market for different microcontroller. So this is a tool from Keil, provided by ARM Holdings. ARM Holdings is one of the company which produces, which designs ARM architecture. It's a CPU architecture. There are different architectures available. We are going to discuss everything. So this is a tool developed by ARM ULIN Pro with you can see one connector over here. That connector, with the help of that connector, we can connect it to the microcontroller hardware. Then we can load the program which we written inside with the help of PC. So let's move to the next slide. What all a microcontroller can do. A microcontroller can sense, process, decide, and control, making it the brain of many embedded systems. You might have seen this device, right? The middle one. It's a coin box. So a coin box is actually an intelligent device. Why I am saying so is because whenever you lift the receiver, it will ask you to put the coin. When you put the coin, it will tell you to dial the number. When you dial the number, it will connect you to that dialed number. When the time expires, it will tell you to put the coin again. So there is an intelligent system inside that which plans everything, which executes everything one by one, sequentially or based on some input. So here, when you lift the receiver, then it automatically detects and tells you to insert the coin. There are so many tons of product available in the world based on microcontroller. You can see automotive infotainment system. In automotive, there are so many ECUs inside the car, inside a particular vehicle. At least 25 to 30 CPUs are there. So every CPU is managed by a microcontroller. Also, there are so many applications in the biomedical industry. Also, you can see so many ICUs, so many devices like modern pressure sensors, like also so many devices you can see in the market based on microcontroller. So a microcontroller is a compact integrated device that contains microprocessor, memory, and input-output peripherals on a single chip. So here, the classification of the microcontroller is based on ISA. So what is ISA? That we have to understand first. So microcontrollers available in the world are classified based on the ISA, instruction set architecture. So ISA determines the available instructions, data types, registers, and addressing modes of a processor. You might have heard, I mean, if you are an engineering student of third year or fifth or sixth semester or seventh or eighth semester, you might have heard instructions, assembly language coding, something like that. So there are so many data types, registers, and addressing modes. Addressing modes means direct addressing, indirect addressing, register addressing. Data types means int, float, such kind of data types. Register means program counter, R0, R1, accumulator, A and B register, DPTR. So many registers are there. So how a particular registers and instructions are available, that is determined by ISA. Also, ISA acts as a blueprint describing how processor performs task via machine instructions, how a particular task is executed via a machine instructions. Next, what ISA does. Instruction set architecture is a key element inside the microcontroller architecture or microprocessor architecture. So based on ISA, it defines the things like tells the processor what to do, how to understand the instruction. Without ISA, software can't talk to hardware. So you have a small high-level code like sum is equal to A plus B. So instruction set architecture converts this ISA code into assembly code. Not exactly, don't take my words exactly as it is. I am explaining the things behind it. The converter who converts C language to assembly code is different one. It is compiler. But inside, even if it is a compiler, compiler should know which ISA, on which ISA the microcontroller is based on. So sum is equal to a plus b will be converted to LDR R0, a, LDR R1, a. These four lines represents this one line. So ISA is the one who acts as a backbone of microcontroller architecture. You will understand it in coming slide in detail. So whenever you think about ISA, here is the diagram. Instruction set architecture is the top one in the abstraction level. So every microcontroller and microprocessor is a semiconductor chip, which is constructed with the help of VLSI technology, very large scale integration technology. So in very large scale integration technology, you might have heard that internally they create circuits. They create combinational and sequential circuit with the help of MOSFETs and some internal registers and so on. So based on that combinational circuit, they create registers and counters. So inside that, registers and counter will be there. On top of that, it will these registers and registers and counters are managed by micro architecture. So above that lies instruction set architecture. So micro architecture and instruction architecture are connected. So you can imagine like ISA as a recipe set of instruction, and micro architecture is a kitchen layout and tools. So whenever you are in a kitchen, you are trying a new dish, you might follow recipe, right? So yeah, based on the recipe, you will take vessels, utensils, oven, stoves. You will use everything. You will use the vegetables. You will use the spices, salt, pepper, everything based on the recipe, right? So like that. So micro architecture is the kitchen and the tools and the kitchen and the tools. Based on the recipe, you are cooking food with the help of the kitchen tools. Okay. Now let's go forward. Yeah, what is exactly micro architecture is doing? Actually, micro architecture is the one who implements the ISA. Who is implementing? Implementing means taking charge of executing things, doing things. So there should be an ISA, instruction set architecture, but micro architecture is the one who implements the architecture. Every CPU in the world, if you check inside it, you can see ALU, address, ALU, memory unit, registers, and cache memory. So it manages the data flow, defines the CPU components like ALU, control unit, registers and register file. Cache means it's a memory inside that, which is the faster accessible memory by the CPU. And you can see pipeline stages, branch predictor. Some sort of CPU internal architecture we will see soon. These are the things which, so that time in your mind, you have to identify, you have to understand those architectures are made by micro architecture based on the ISA, instruction set architecture. So what does it do? It optimizes the performance like pipelining, parallelism, superscalar execution, out of order execution. These are the performance related functionality of the instruction set architecture. Moving to next slide. So in the world, microcontrollers are classified based on ISA. So we have 5 different major instruction set architecture. Not 5, 4. Okay. Those 4 are CISC, RISC, VLIW, and DSP. So CISC, you might have heard complex instruction set computing, which has large number of instructions, performs complex tasks like multiplication, memory access, etc. in a single instruction. RISC you might have heard nowadays reduced instructions computing, fewer simpler fixed length instruction. Most of the current microcontroller are based on reduced instruction set computer, which is ARM Cortex M series ARC64 based controller 𝗬𝗘𝗘𝗘𝗘, and 𝗫𝗏, the advanced microcontroller, which is open source. So VLIW, very long instruction word microcontroller, execute multiple instruction in a single cycle. So this is used for digital signal processing, and there is one special uh, architecture for DSP also. So it includes MAC, multiply and accumulate, barrel shift register, etc. inside that architecture. Nowadays, companies combine the architecture, or they define their own architecture. Like my previous company, Infineon Semiconductor, they had one particular architecture called a Tricore. That is a proprietary architecture by them. So made by them. So every architecture, if you see, and if you open and see the architecture specification, you can see these many parts available in almost all the architecture. So ALU would be there, CPU, CU would be there, memory unit, cache, registers would be there. So let's go to the next slide. So I am focused on this session only on two type of ISI, that is RISC and CISC, because it is the leading architectures available in the market. Most of the controllers, almost 75% of the controller is made by RISC, and few are made by CISC and other ISA architecture. You might have used the CISC architecture-based processor and controller, that is 8085 and 8051. RISC controller nowadays you can see as ARM architecture and 𝗫𝗏 based controller. So what is RISC and what is CISC? Actually, RISC uses many simple instruction like load, add, store, etc. These are assembly language instruction which I am telling. So whenever you program a microcontroller, just open Paint for everybody's understanding. I am on Paint. Let me explain where Paint. So if you have a microcontroller, you can program it in different ways. Like you can write a code on machine code, which is a combination of zeros and ones. Then you can write code on assembly language, that is combination of like assembly language instruction like move, a comma, p, something like that. Then you can program it with the help of C programming language. There you write a equal to c plus d. So, or you can write something meaningful in English, like you can use the printf kind of statement for printing the messages. Printf, inside that printf, you will write something, right? So these are the way you can interact with the microcontroller. One, you can directly program with the help of machine code 0 and 1. That is highly impossible, error prone, difficult. Assembly is comparatively better if you are comparing with machine coding. C is the high level language where globally we used to program microcontroller. So when you write a C program, there you need so many tools in order to that that code converted into machine code. Okay, so come back to this one. So RISC architecture, they are telling this load, add, store, similar kind of reduced instruction set computer. So RISC means reduced instruction set computer. So it has very less uh, assembly language instruction available for programming the chip. But CISC has many instructions, and it has lengthier instructions which can take more time, to execute a particular instruction. So in case of execution time, RISC is leading. So I have a question to all of you. Just comment it in the chat. Which one would be better, RISC or CISC? Just type it in the comment what you think. I am telling that see the image and see. In RISC, it has to see. We have a cook here. He is preparing egg omelette. So what he has to do is he has to do everything. He has to take the egg. He has to add the pepper. He has to stir it. He has to boil it using the pan. But here on the right side, you can see a particular machine which does all these things for you by pressing a button. It will automatically do everything for you. So I am telling this right side is CISC1, left side is RISC1. So based on this image, I am telling that RISC uses so many simple instructions. So suppose for multiplication, it has to do multiple addition. So there is no mul command available in RISC. But there is mul command available in CISC. So in the chat, you have to mention which one should be the better instruction set architecture. Vivek asked me, depends on the scenario. Vivek said, depends on the scenario. Aisha is telling might like depends on the application. You change according to the situation, right? More answers I need, or more questions. Whether I am just asking whether it is RISC or CISC. Which one would be faster? That is the right question. Yeah, you might be seeing it as CISC.
Hello.
Okay, let's continue. You will understand why the one which we talked about is better compared to other. So these are the major architecture available in the world. Like RISC is leading now. CISC is there as x86 processor. You might have heard x86 architecture that depends on CISC. Let's move to the next slide. So here the winner is actually RISC chip. RISC simplicity wins in terms of performance, power efficiency, design clarity, and scalability. So there is an equation for every microprocessor should execute the instruction by taking lesser execute time. So that is the reason why RISC created reduced instruction set architecture. So CISC you might feel like it can do the things. It can do the things in a simple stretch, like multiplication can do it in a simple simple one instruction execution less, just like this machine is preparing omelette. Then here the equation you can see 1 by clock rate into CPI into instruction count. So whenever the instruction count increases, cycles per instruction and clock rate depend cumulatively makes the execution time higher. When the instruction count increases, execution time increases. But if you see cycles per instructions, CPI is getting reduced, or any part here, if the clock rate is increased, you will get the execution time lesser execution time you will get it. And if you have cycles per instruction less, you will get lesser execution time. Also, if you are having instruction count lesser, you will get lesser execution time. So most of the nowadays microcontroller or manufacturers are trying to reduce the execution time so that it can execute millions of instruction in nano or millisecond time. So what they are doing is they are increasing the clock rate. They are decreasing the cycles per instruction. Also, by code optimization, they are reducing the instruction count. So code optimization is done by the compiler or the tool which the embedded system developer develops the code. So these are the things which determines the winner, which is 𝗓𝗃. So it is the winner here. So now let's proceed to next slide. Yeah. Now we are going to learn about two different architecture, that is ARM and 𝗓𝗃. ARM and 𝗓𝗃. Both ARM and 𝗓𝗃 are different architecture. Don't get confused. RISC and CISC is architecture. Okay, RISC and CISC are two instruction set architecture, ISA. Here, I am going to explain ARM and 𝗓𝗃 architecture. Both are RISC architecture, ISA. So this is a microcontroller's CPU name, and this is another CPU name. I will explain it. ARM is a CPU, or ARM is a central processing unit or a microprocessor manufactured by ARM Holdings. Okay, ARM Holding is a company, a US-based company who manufactures, who designs. They are not manufacturing any chip. They might be manufacturing for their internal purpose in order to study R&D purpose, but they are not manufacturing any microcontroller or processor for the open market. Okay, so ARM is a company who designs CPU and they sells it outside. So from ARM, Qualcomm will buy. From ARM, Infineon will buy. From ARM, NXP will buy. So there are so many microcontroller vendors available in the market. They all buy the CPU architecture from them, and they will accumulate all other peripherals, like so many other peripherals, you know, right? I2C, SPI, UART, CAN, LIN, some other memories. They incorporate all the memories together with the ARM CPU, and they will manufacture the microcontroller. 𝗓𝗃 is also based on 𝗓𝗃 ISA. 𝗓𝗃 ISA. So 𝗓𝗃 is an open source architecture, which means they have made all the Verilog code available in the website or in the public domain. They made all the Verilog code available in the public domain. You can download it from the website and you can make it your own microcontroller or your own processor. So 𝗓𝗃 is an open source microcontroller architecture. ARM is a what we can say, ARM has its own proprietary architecture. They don't sell the architecture. They only sell the IP related information, internal code and all. They keep it as their own proprietary secret. They don't give that internal details. So How these ARM and RISC are manufactured based on the VLSI design process that you should aware of it. Like VLSI microcontroller manufacturing is a part of VLSI design process. So there you write your own design with the help of Verilog code, right? So every design would be available at the first stage. It would be Verilog code. So there they manufacture it with the help of different steps. That is not that is not the scope of this discussion. It is not part of this discussion. We are proceeding like to architecture, that is ARM and RISC-V. So ARM gained popularity through power efficiency, licensing flexibility, and ecosystem maturity. What is mean by that is like most of the microcontroller available in your mobile phone devices are now ARM CPU based microcontrollers like Qualcomm and iPhone's latest processor. I forgot its name. It is also based on ARM 64-bit processor. So here you can see in the first picture, the cook, he is already famous, just like ARM gained popularity through power efficiency, licensing capability, and ecosystem maturity. And one guy, he is right now learning how to prepare dishes. So he is using his own kitchen, his own equipments. So he is currently gaining popularity by his own experiments. So it's being open, customizable, and cost-effective, fitting the needs of modern computing diversity. In near future, RISC-V will overtake ARM, just like Linux did on top of Windows. So it is going to happen because RISC-V is open source. So many R&D enthusiasts will be taking this RISC-V architecture, and they will be working on top of that RISC-V architecture in order to make their own microprocessor and microcontrollers. Now let's proceed. This discussion is based on ARM architecture. Okay, so now when I am proceeding from the next slide, you will see that I will be discussing most of the things related to ARM architecture only. Any questions? Just waiting for some questions. If you have any questions, you can ask. I will wait for some 15 seconds if some question is coming. You can turn on your mic and ask if you want, or else we can proceed. Okay. No questions.
Sir?
Yes, continue.
Okay, sir, if the RISC-V architecture is taking over the ARM architecture in the coming days, will it be relevant to study the ARM architecture?
Yes. Yes, it is relevant to study the ARM architecture. Why? Because most of the architecture I said in this previous slide. Just a second. I said in the previous slide, here you can see every architecture has microarchitecture, implements ISA. Every architecture consists of a CPU. It has internally the things, everything's as the same. ALU, CU, memory unit, cache memory, registers. If you know one architecture properly and the associated tools, everything will be same. Just like ARM architecture, it has RISC-V architecture also has same internal steps, but how they connected, how they planned those circuits internally, that makes the difference. So we don't know how ARM has created its microprocessor inside, like what is their Verilog code. So ARM is a big company. They have their own people who accepts huge salary and works for ARM. So they are a huge system. They gained so much popularity with their engineers inside. So it will be there for a few more decades. ARM will be there for a few more decades. RISC-V is still gaining its popularity. So I have seen like most of the companies right now, like Infineon started manufacturing their own processor based on RISC-V, also NXP, Qualcomm, everyone is going behind RISC-V now because it is open source, because they can create their own CPU. They don't have to depend ARM in future. If ARM is telling that we need this much proprietary license, company will be screwed up, right? So this is the thing which happens right now. So if you are learning ARM, it won't be a waste. It will help you to learn RISC-V faster because everything, the tool, the process, the internal steps, everything is same. The difference is how it is planned, how it is getting uh, available inside the controller. So I have heard that people are telling nowadays Kerala's engineering syllabus or even in India's engineering syllabus is not up to the requirement of not up to the requirement of the needs of industry, but it is not that much true. If you know the basics, if you know the fundamental, you will be able to catch up things as quickly as possible. So that's why I have kept this slide here. Architecture of 8085 based CISC. Architecture of 8085. 8085 is an old processor from Intel. It's based on CISC, complex instruction set computer. So let's go through that. You can see the sixth point. Control unit orchestrates everything using clock and control signal. So you can see one particular block here, timing and control block. You can see some associated blocks also, like arithmetic logic unit, accumulator, temporary register, flag flip-flop, instruction register, instruction decoder and machine cycle, then multiplexer, associated stack pointer, program counter, increment, decrement, address latch, address buffer, data buffer, address bus, data bus. Also, some external signals lines are also available. INTR interrupt, INTA serial data in, serial data out. Now, just I am going to the next slide. You can see one schematic, 8085 based hardware and hardware schematic. Here you can see this is the 8085 microcontroller. You can see this is 8085 microcontroller. Its address bus and data bus is shared. You can see this thick black line is connected to memory via a latch. Is connected to memory via a latch. You might have heard latch. Latch is a particular IC which can hold the data even if the input got changed. So here you can see it is connected to ROM, and here it is connected to RAM. So for this processor, RAM and ROM is outside. So this is some schematic of some project or something which blinks LED or something. It is doing something like turning the LED on or something. So if you wanted to have a product based on 8085, you have to interconnect external ROM, you have to connect external RAM, you have to provide few more subsystem chips like latches in order to work the 8085 chip properly. So this makes the system more complex. That is why microcontroller is in the market. So what they did is like they incorporated this microprocessor with the associated peripheral. Let's check how this controller works actually. So the controller working, you might have studied like instruction set fetched from memory using PC and address bus. You can see using PC. PC is this one, program counter. Whenever the microcontroller powers on, you have heard program counter will be its initial value 0, 0. From there, it will start fetching the data, fetching the instruction from the external memory. External memory in the sense, here you can see this is the external memory ROM, where we place the code, executable code, we place it here. So whenever the microcontroller powers on, the PC will try to access the executable instruction code through the data bus. You can see here there is an internal data bus connected to address bus and data bus. Address bus will provide the address. Through data bus, it will get both address and data. See, here it is a 8 into 8 address lines. 8 into 8 means 16 address lines. You can address it up to 2 raised to 16 bits addressable memory you have. So with the help of the 2 raised to 16 memory location, you are trying to access few instruction. That instruction will go to instruction register. So from there, instruction register will feed those instruction into instruction decoder. So instruction decoder will decode your instruction which was there in the ROM. So that ROM instruction will reach here, instruction register, then those instructions will get executed. It will be executed by the ALU, arithmetic and logic unit. So it will access data. So whenever if you are writing something like x equal to a plus b, it has to read data from A, right? So accumulator will go and collect the data from data memory like RAM. It will collect data from RAM, and it will perform the arithmetic and logic operation. It will again write it back to the memory RAM, not to the ROM thing. Random access memory, which helps you to retain the data during the controller execution. So what each step happens, data is fetched from or written using ALU, accumulator, and general register. Result goes to accumulator and flags are updated. Results goes to accumulator. If you want, you can write it back to RAM by using instruction. Accumulator holds the result, and you can write it back to the RAM, SRAM, static RAM, with the help of your instruction. Move A comma B, like move A comma some external address you can provide, and by that way you can, or move external address comma A, you can write it back to that external memory. So this is what happens when inside the processor, okay, inside the CPU. Now let's move on to next slide. We have two different memory or system architecture available in the world. That is Harvard architecture and von Neumann or Princeton architecture. Harvard architecture is the better one because it has dedicated address and data bus separately for data memory and code memory. You can see that it has data memory, it has the CPU has to access data from data memory, CPU has to access data from code memory also. Code memory, the data would be instruction code. Inside the data memory, the data would be the code which CPU has to perform or read or write. It is data, it is code. Here also we have code memory and data memory, but there is no dedicated bus lines. It has to read it through the same address bus and same data bus. There is no dedicated lines, address or data lines available, just like as in Harvard architecture. So most of the latest controller or processor are based on Harvard architecture. Okay. So this is the memory system architecture. Now we have processor microarchitecture. So processor microarchitecture is based on how the CPU is planned, to execute the instruction. So we have one we have one pipelined architecture and we have one superscalar architecture. So I will try to explain pipeline architecture. You can see here the instructions, first instruction, second instruction, like that you can see. Here you can see the clock cycle as well, T1, T2, T3, T4, like that. So at the time T1, instruction is fetched. IF means instruction fetched. Then it moves to the other time. So here, you know, the clock cycle, right? Clock cycle is nothing but you can imagine something like this. Every second, your microcontroller external clock is provided by a crystal or something. You might have heard an oscillator circuit, some circuit which can produce these kind of signals, clocks. So based on the clock, you can see that at time T1, instruction is fetched. At time T2, the fetched instruction is decoded. Also, a new instruction is fetched. At time 3, the current decoded instruction is executed. Also, the previously executed instruction is decoded and new instruction is fetched. At the time T4, it might read or write the data based on the instruction. At that time, it execute the instruction which was previously decoded, and it will decode the execution. It will decode the data which was previously fetched. Also, it will fetch a new instruction. So this is a cycle which repeatedly happens. This is called pipeline. So every time, whenever a clock is proceeding, it will fetch a new data. So this is called pipeline architecture. There are you can learn how pipeline architecture is created. There are two types of learning the internals in the way of VLSI design expert, or learning the way of things as an embedded expert. Okay, what I mean by this statement is that, suppose if you want to learn pipeline architecture, if you wanted to learn it in depth, the VLSI concept of implementing pipeline architecture would help you. Suppose if you wanted to know how pipeline architecture is working as an embedded perspective, you have to just understand what are the different blocks inside a pipeline architecture, how it is working. That might be enough for you. So next processor microarchitecture is superscalar architecture. In that superscalar architecture, you can see different blocks. There is an instruction fetch unit which should be there in the pipeline architecture. There is an instruction queue architecture instruction queue unit which is there in pipeline architecture. But in superscalar, there is a dispatch unit, floating unit, integer unit, and write back unit. So we have a instruction fetch unit, instruction queue unit, write back unit available in pipeline architecture. It might be there or it will be there. But in superscalar architecture, there will be a dedicated dispatch unit, floating point unit, and integer unit. So what dispatch unit does is, it will identify the instruction. It will identify the instruction by searching in the instruction queue. If it is a floating point type of instruction, it will feed to floating point unit. If it is an integer kind of instruction, it will feed to integer unit. So the execution will be happening much faster than the pipeline architecture. So the latest microcontrollers, microprocessor are following superscalar architecture. So many variations would be there. People will be making progress of the internal circuitry of the controller by doing so many R&D work. So they will combine things for most efficiency. So they will use pipeline, they will use superscalar, they will mix up things. So this is how the industry evolves from the basic old stuff to new stuff. Okay, so that is what VLSI experts do in the industry. So ARM architecture. So I'm going to explicitly tell about ARM architecture. So inside ARM architecture, I have have only got this picture because I have told you already. ARM is a proprietary architecture. They don't reveal everything they created inside the architecture. So as I said, every architecture, just like every architecture, it has instruction decode and control unit. It has separate address bus. It has separate address bus. It has separate data bus, just like what we have in uh, Harvard architecture. So you can see the address register. There is a dedicated bus inside this A bus, address bus, and data bus. Also, we have the program counter. Everything, whatever we have seen in 8085 microcontroller, 8085 microprocessor or CPU, you can see everything inside this ARM architecture. So everything is common, but how the instruction is fetched and decoded is maintained by instruction set architecture. That is what RISC architecture and the CISC architecture is doing. That from manufacturer to manufacturer, it will change. If you are using ARM architecture, it will follow this one. Or else, if you are using RISC-V architecture, it should be like this. Here also you can see the execution pipeline. You can see the fetch module, pre-decode module, decode optimize module, execute module, memory access module. So many modules you can see. It has also everything like there we have in 8085. But here you can see instruction interface, data interface, debug unit, uh, branch predictor, data cache, CPU state. Also, it should have the ALU and all other basic stuff which should be there in the CPU. Moving to next slide. So yeah, we have reached to microcontroller architecture. As I said, microcontroller is a chip which incorporate everything. Incorporate everything means not everything in the world. Incorporating the essential things in order to make the chip compact. So there is a CPU. So common microcontroller architecture, you can see one CPU that can be ARM, that can be RISC-V, that can be DSP, that can be VLIW, that can be Infineon Tricore. The CPU should be there. That is the head of the microcontroller, which collects all the information, which executes the instruction, which writes to the peripheral, which reads from the peripheral. Everything is done by the CPU. It has the dedicated oscillator circuit you have to provide. Also, everything is internally, not just like this one. Not just like this one. It has everything internally. Everything internally. RAM is there, ROM is there, timer, so many peripherals are there. So this is a common microcontroller architecture, a basic one. Moving to next slide. So this is ARM-based microcontroller. You can see ARM processor, ARM CPU here. So ARM processor, you can see here, it is accessing data with the help of different bus. Suppose you wanted to learn ARM architecture in depth, you have to understand two buses, that is AHB, advanced hyper bus, and APB, advanced peripheral bus. So APB, you can see in APB, you can see so many peripherals are connected here. See, Ethernet, MAC, CAN, USART, USB, SPI, PWM, ADC. So if your company wanted to incorporate some audio, so audio chip like TDM, I2S, these are audio interfaces. So audio protocol. So if they wanted to incorporate audio a processor, a microcontroller with the audio feature, what they will do is they will buy ARM processor proprietary rights from ARM Holdings. They will get the code and everything. They will get the IP. So what they do is they will buy the IP. They will buy audio IP as well from some analog devices, and they will interconnect it. or they will create their own audio IP with the help of their VLSI design engineer. So they will interconnect it like this. So ARM processor has its own dedicated AHB and APB bus bus availability. So APB bus is used to connect peripherals, just like SPI, UART, CAN, the one which I told, audio. So every peripherals are connected in this one, in this APB bus. Then which would be at working at lower speed. Okay. So if you want something with a higher speed, it is connected at AHB. You can see all the memory controller are connected, or all the memory controller and memories are connected at AHB directly through memory controller. See, SRAM, flash, internally, everything is internally now. You have RAM inside, you have flash memory inside, flash programmer control circuit is there. Some data will come inside and flash memory will get updated. We will learn about flashing and all those things later in the coming lecture. You can see some associated peripherals also there, associated units also there inside that. That is system controller. You can see programmable phase locked loop, oscillator, RC oscillator, reset control, burnout detect. So many other circuits are there in order to support the microcontroller during power on, during some failures, like watchdog timer, debug unit. So if you are learning microcontroller, you have to learn a particular architecture like this. You need to know what individual units does. Something like that you have to focus on. So these are the two buses which connects memory and peripherals to ARM processor. Now see the same RISC-V based microcontroller. RISC-V based microcontroller, you can see RISC-V core here. See RV32EC. See this one, RV32EC. It is connected via a bus, that is AHB bus here. See, on AHB every peripheral is connected, but in ARM architecture it is connected on APB, right? So here you can see they connected everything on AHB. It is their wish. It is their wish. This is some microcontroller. This is some microcontroller's internal architecture which is based on RISC-V. See here the difference you can see. It is connected on AHB. So that is what I said. It is depend upon your company's wish whether to take ARM microcontroller or ARM processor or RISC-V processor, ARM CPU or RISC-V CPU. So you are making a RISC-V based microcontroller, you can easily take RISC-V architecture from the website. There is one GitHub link. From there you can download all the Verilog code. With the help of that Verilog code, you can implement RISC-V architecture. You can connect an 𝗫𝗫𝗄 module with the help of an ASB data bus implementation. Something like that you can do. You can make your own chip if you are an intelligent Verilog coder. Not intelligent, if you are a consistent Verilog coder or a Verilog learner. Now, internal connectivity, how peripherals talk to CPU. See, how peripheral talks to CPU. CPU is a brain. Here, this guy has his brain, so that we can treat as CPU. He has his hand. He has a fist. He wanted to punch someone. He wanted to punch someone in his face. So what he has to do? His brain has to tell to do that, right? So CPU acts as a brain, and peripheral acts as peripheral can be treated as example as his hand. Now just move forward. See what happens. Internal connectivity. How peripherals talk to CPU. Just ignore this P. That is a mistake. Okay. CPU. CPU first talks to AHB bus. Okay, I am talking everything based on ARM architecture now. CPU first interacts to ASB bus, then ASB bus interacts to ASP to APB bridge. So from AHB to APB bridge, it is connected to peripheral. This is how the data transfer happens from peripheral to CPU and CPU to peripheral. There is a pathway, that is this one: CPU, AHB bus, AHB to APB bridge, and peripherals. So here you can see ARM processor wants to talk to CAN peripheral or USB peripheral. Okay. So what it has to do, it has to initially take the path of ASB, then it has to go through the peripheral bridge. So there is some internal Verilog logic which switches the bus to interact with APB. Some kind of multiplexing it does there. With the help of that multiplexing, ARM processor will get peripheral bus. If the multiplexing is in other way, it will get memory or something like that. It is happening inside there. So APB bus will be enabled, and some CAN information will be read through APB bus. It will come through peripheral bridge, and it will go to ARM CPU via AHB. So this is what happening inside the ARM processor when it wants to communicate with the peripheral. If the ARM CPU want to punch someone's face, it has to send the signals via this to the peripheral. Okay. Now moving forward to microcontroller booting process. Till now, we were discussing about the hardware. Now we are gradually switching to the software tools which is associated in building the software. So you can see in the picture, a kid is trying to wake up the dog in the morning. Okay. So what happens when the dog wakes up? It starts making sound. It starts creating sound noises. It will start running all the way through the room, right? Just like that, microcontroller also do the same. On power on or on reset, it initially fetches a particular information. Microcontroller fetches reset vector from vector table, which is located at 00000, or as defined in the linker script. You will understand what is linker script, what is vector table in the coming lecture. Okay, I can't go in that way. First, I will explain linker script and coming back the boot process. But eventually, you will understand the boot process clearly. So, microcontroller booting process is started on power on. When you apply power, I will show you one thing. Just I am taking my simulation. I'm audible, right?
Yes, sir, you're audible.
Yeah, I have a question here. Sir, you have told that ARM and RISC-V architecture are different from classification between RISC and CISC architecture. Okay. How can I explain this? See, RISC is an ISA. See, RISC is an instruction set architecture. As I said, we have different kind of instruction set architecture. See, this is the classification of microcontroller based on ISA, that is CISC, VLIW, DSP. So CISC is an architecture, RISC is an architecture. Which architecture based on ISA? I mean, based on instructions in architecture, they are calling it as CISC and RISC. Okay. So CISC holds a different kind of instruction set architecture. RISC holds a different kind of instruction set architecture. So what I have told is that, see, RISC, ARM and RISC-V architecture, both are RISC-V architecture based processor. Okay. ARM is a processor. RISC-V is also a processor. Okay, they named it RISC-V. They could have taken some other name. I don't know why they made it complicated to understand. So ARM is an processor which is based on RISC-V ISA. RISC-V is also a processor which based on RISC ISA. So both the processor use the same instruction set architecture style. but the underlying architecture of underlying manufacturing architecture may different based on their approach. They can use different approach to manufacture, but they both are using reduced instruction methodology. The number of instruction is made reduced in order to get the execution time lesser. I hope I answered the question. If you need more clarification, you can make the question more proper so that I can answer it and accordingly, according to your question. Okay, so let's move forward. I wanted to show you something. See, this is one small circuit which is going to execute a code. So here you can see I am using a microcontroller called STM32F103, which is based on ARM processor. STM32F103 has a ARM processor inside. So just I am powering it on by hitting this play button. Okay, so you can see this LED is blinking. So which means that something happened during the power on. So it was dying or it was lying on the bed, just like that dog seen in this picture. So what I am doing, just like that kid, I woke up this microcontroller. So after waking up, the microcontroller is executing a particular code. Okay. So it is executing a particular code inside that microcontroller. Now we are going to examine few more things. So, see, power on. See, after power on or reset, microcontroller fetches reset vector from vector table. Okay. Muhammad raised your hand. Anyone have questions? They can ask. No, right? Okay. Okay. So what happens? I'm continuing the booting process of the microcontroller. When someone powers on the microcontroller, what actually happens is that inside the microcontroller, there is one particular circuit called reset circuit. You can see here reset control. This is the microcontroller, ARM-based microcontroller architecture figure. Inside that, you can see one reset control unit is there. It detects brownout detection, power on reset. So there is one circuit which is called power on reset, which detects power on. At the time of power on itself, microcontroller gets a reset. What happens when a controller resets? I will show you. On power on or reset, microcontroller fetches reset vector from vector table. This vector table is located inside the flash memory. So where is flash memory? I have to go back to the microcontroller lecture again, slide again, but I am not going. You have to keep it in mind. The flash memory is inside the microcontroller itself. Okay, it is not external, just like as we had in 8085. It is not external, it is internal to the controller, connected to AHB bus. It is directly connected to AHB bus. So flash memory, inside the flash memory, we have a code. From that code, it fetches reset vector details. Then from there, it executes a startup code. Now it is my turn to go back to a code where you can see. So this is the code. I hope you can see the code. So in line number 21, you can see there is a header file, main.h. When you go down, you can see some function system clock config, mx GPIO init, then main routine. There is a hardware abstraction layer init, system clock config getting called, in GPIO init getting called. Then there is an infinite loop with the help of while one. There is a code inside that while loop which helps blinking the LED. So that is this two 4 lines. First line, it is setting a pin. Second line, it is giving a delay. Third line, it is resetting the pin. Fourth line, it is creating a delay again. I am not here to teach you the C programming code. My today's aim is to tell the behind the scenes, the compilation, and what are the associated steps related to the code creation process. So every microcontroller project should have a main.c. So that is inside this src main.c. So this is the file which tells the microcontroller to do something after power on. Okay, so this is what happens. It is continuously blinking the code, but there is a particular code which is startup code. Startup code does these many things. It sets the stack pointer, copies .data to RAM, zeros out BSS session in the RAM, then calls the main function. You have seen a particular main function written over here, right? This particular main function is called after several processes. After completing set SP, after copying .data to RAM, after copying zero, after creating, after clearing the BSS session in the RAM, then it calls the main. It is the duty of startup code to call the main function. So this happens when it powers on. So startup code sets the stack pointer. It copies .data. .data means the local variables which you created during the program creation. Just like you do, right? Int x equal to 10, something like that you do, right? So that all is done by startup code. Then it calls the main user application. See. So this is the process. Now I am here to explain memory layout of the C program. You can say like that, but it is the memory layout. So text and code segment. So you can see lower address. So this is the lower address. This is the higher address. Just ignore this one. I don't need that. This is dedicated to software coding, where you code the software for operating system based coding. You will be using this one. So whenever you are using operating system based C code development, like whenever you are developing some software code for Windows application or Linux application, this command line argument section is valid. If you're an embedded software professional, you no longer need that particular section in C. So I am going to explain this one, lower memory address. So we have two memories, right? We have two memories. I have to go back to slide, please. So we have two memory. One is this one, SRAM, static random access memory, which is volatile. And we have this one, flash memory, which is a permanent memory, just like EEPROM, ROM, something like that, which is permanent, volatile and non-volatile memory. So going back to it is difficult to go forward. Yes, yeah. So this text or code segment, which is the code which you wrote. I mean the code. This is the code. So after compilation, just like compiling, for the compilation, I have to just click this button, this hammer sign. You can see, right? So this is an IDE, software development platform. There you, after writing the code, you have to just click this button in order to create the executable file. Okay. So after clicking that button, you will get one .hex file. I will show you that code. So here you can see 𝗏𝗏𝗖𝗏𝗏. I am opening that one. So inside that particular file, you can see machine code instructions. I have already told we have wrote the code in C language. At the end, you are going to get the machine code, which directly executes in the microcontroller. So we need a dedicated hardware in order to copy this particular code to the microcontroller. That is called programmer. I have shown you one figure at the slide number 2. when I am explaining the microcontroller, what is microcontroller, that slide. So, so that hex code will reside in the lower memory address area of the entire memory. Entire memory means RAM plus ROM, I am saying. So inside the ROM memory, at the lower memory address, you can see text or code segment. After that, these all belongs to static memory layout. Okay, these memory allocation won't change during the execution of the code. When the microcontroller turns on or the powers on, the memory created on this section won't change. Okay, so that is initialized data segment, uninitialized data segment, something like that. Initialized data segment means you are creating a global variable using a C code like int x equal to 10 in global area that will be resided inside the initialized data segment. Uninitialized data segment is a global variable which does not have any value, just like int a. It does not have any value. That is called BSS session. Then you have a dynamic memory layout, just like this one, dynamic memory layout, where you have different kind of memory like stack and heap. Stack starts at a higher memory address and ends at lower memory address. Heap starts at lower memory address and ends at higher memory address. When stack, you know, right? Stack is the memory location which uses when function call is happening or interrupt happens. We need to push some information which is executing locally in order to save it. So stack is the one which holds the temporary value. Just whenever there is a function call, suppose you are executing a main routine, just I will open the code. Suppose you are executing this main routine, some interrupt comes, it has to go somewhere, right? Here, see, here HL in it is a function, it is getting called from the main function. So it has to jump to that function, right? HL, see, this is HL init. See, this is GPU init. See, there is a code for GPU init. So it has to jump to that location. So at that time, it has to save some temporary information which was there in the main routine. So that this kind of information is stored inside the stack memory. So stack memory will have the local variables, will have the stack pointer value, will have the program counter value. So many temporary things will be stored in the stack memory. Heap memory is for his memory is dedicatedly used during the execution. Sometimes you wanted to receive an image, but you don't know the size of image. So you have to plan the memory based on your requirement, right? So at that time, there is some feature available in the C programming that is called dynamic memory allocation, which is done with the help of two functions, that is calloc, malloc, realloc. So there are so many features available in the C code in order to manage this heap section. So this is a runtime manageable memory area. These two are managed during the runtime, which is dynamic. The size of the memory unit will change entirely. These all things will reside inside RAM. Text code will reside inside flash memory. Okay, so this is what I wanted to tell you about the program memory layout. Without this, we can't proceed. Anyone have doubts here? I have no idea about the attendance. No idea. Uh, can any coordinator pitch in and okay? Thanks, Niranjan. Yeah, I'm proceeding. So see, this is the memory map. Previously, we talked about memory layout, which is managed by software, okay, which is managed by the compiler with the help of a linker script. I will explain what linker script is. Program memory layout is managed by software, okay. Software. It's difficult to write with mouse. Software. But here it is hardware, understanding the memory map. So here you can see in the lower address, it is the code area where it belongs to flash memory. Then it comes to SRAM, then it comes peripheral, then it comes external RAM, then it comes external devices, then it comes some private peripheral bus, vendor specific information, peripheral, private peripheral bus external. So our interest is lies on this area. Okay. So here is the code area, which is 0.5 GB, 512 MB, and SRAM you have 512 MB, peripheral is also 512 MB. So here lies all this information belongs to the microcontroller peripherals and the internal memory. So what happens whenever you wanted to blink an LED? So here you can see this LED is getting turned on and off, right? It is getting turned on, it is turning on, and it is turning off. So something is happening. What is that? I will tell you. So here you have the peripheral, right? So one among this peripheral, it is GPIO. So we have so many peripherals like CAN, LIN, FluxRay, so many other peripherals like GPIO, ADC. So ADC, GPIO is one among the peripheral which lies at address 0x401 000000. Okay. So imagine that your GPIO pin belongs to this particular address. What you are doing is your CPU is writing a 1 at this particular address. This is what happening when this LED illuminates. See, when it writes 0, it is turning on. When it writes high, it is turning off. See, so what happens is like see, this is our architecture. So imagine we have a GPIO, maybe see, this is our GPIO. So it is configured as general purpose input output. Then it will CPU will access this GPIO with the help of these lines AHB, APB, peripheral bridge. So our code is telling the CPU to make the GPIO pin high and low. So what it does is that CPU know the address of that particular GPIO. It will write 1 and 0 in between a particular duration. That is what the delay does. So what it is doing is it is writing a 1 and 0 to an address that is somewhat like this 32-bit address. So this is what happens inside when an LED blinks. So someone is writing, not someone, CPU is writing 1 and 0 over here in between that delay. So you can see this code. See, GPIO write pin set, GPIO write pin reset. In between there is a delay. So there is someone who is converting this high-level logic into low-level machine code and gives you this kind of code. That is compiler and its associated tools. We are slowly moving to those tools. So before going to those tools, you have to understand this internal concept, what actually happening. You need to know the program memory layout. You need to know the memory map. If you are an expert of analyzing this memory map and this program memory layout and coming tools and support code, you will be an expert embedded coder or a microcontroller expert. Now, let's go to startup code. What is startup code? I have said previously in the slide that say microcontroller fetches reset vector information and it executes a startup code. Okay. So what is startup code doing? It is setting the stack pointer, copy data from SRAM. I have told it, but still, see, set up the stack using eStack. I am opening that. I'm opening one startup code. So this is how the startup code looks like. It is in assembly language code. See, here you can see from line number 10 to line number 15, it is it is setting the stack pointer. It is setting the stack pointer. Now what is doing? It is jumping to the reset handler. You can see section reset handler. So you might be thinking, where is this stack and where is this reset handler? All these things, where is it mentioned? It is mentioned in the linker script. Okay, I will explain linker script later. So this is stack and reset handler initialization. Now what does it do? It copies data. It copies data from flash to RAM. What kind of data? You have initialized so many local variables and so many global variables and values, right? So it copies data. See, after reset handler, it copies data from flash to RAM. See, these are the copying instruction from flash memory to RAM. Okay. Now what is next? Zeros out BSLs. Uninitialized variables are getting zeros. So see, zeros initialize BSS, init BSS section. So init BSS section, these are the flags. Okay, so here you are calling this particular function, or this particular function is executed after the microcontroller powers on. So this is the sequence what happens in the startup code. So in this section, this section is zeroing out all the uninitialized variables. Suppose you declare a variable int x semicolon, it has to be zeroed out. Okay, so that is what this section is doing. Then it calls the main. Here is the function. Here is the particular area where the main function is getting called. If some trap is happening, something happens to the microcontroller execution, like hard fault or something, it will some hanging loop. If some hard fault, if you are trying to access a memory which is invalid, it will go to hard fault. So sometimes your code is trying to access a memory which is no longer there. It will create an hard fault to the controller. So that time it will hang the processor into an infinite loop. So this is that section handling that hanging area. So let's go back to the slide. This startup code. After that, we have the linker script. So it tells the linker. Who is the linker? It's a part of compiler. It's a part of compiler tool chain. So linker script is the one who scripts how to. So you can see an image here. He is the person. He is the script writer. So see, he wrote a script. Telling to the compiler that where to put the code, comma, the interrupt service vector, where to place variables like x, y, z, a, b, where to set the stack pointer, what needs to be copied from flash to RAM at the runtime. So these many informations are copied with the help of linker script. These things are done with the help of linker script. So during the compilation time, compilers one among the tool is linker. So compiler has different tools inside that. One is compiler. I don't know why people are making names like this. They could have renamed name of compiler in a different name. So let me tell you, compiler has different tools. These are the code compilation process. First one is pre-processing. During pre-processing, then it is compilation, then it is assembling, then it is linker, then it is generation of hex or bin code. See, during the compilation, these entire things are called compilation process. Okay, an entire tool in collective is called compiler. But who is actually the compiler? This unit is the compiler. Okay, This unit is actually the compiler, but we call everything as a compiler, but it is not like that. So this is a preprocessor, this is assembler, this is linker, this is some code generator you can call. Okay. So linker is the one who works based on linker script. So linker is the one which decides where to put the .txt section. So .txt section should reside at lower memory address where the addressing starts. We have seen the address starts at 000. Sometimes it will alias to some different address. See, you can see. No, I am not going to tell that. That will make some things complicated. So just listen. Just imagine that the address starts at 000. So yeah, we'll proceed to this one. So pre-processing. So during pre-processing, what it happens? I'm going to explain that. See, this is our high-level code. You can see there is one particular line at line number 20. You can see hash include main.h. You can see some something in the code like hash define LED equal to something, LED equal to P1, something you will write. So in embedded. So these are the things which is taken care by pre-processing stage. So what happens in the pre-processing stage is it will comment out, it will remove the comments. You have given so many comments here, right? With the help of slash dot and dot slash. So it will remove so many comments. It will expand the macro. This is a macro. It will include the files which is added with the help of include.h. So many things will happen during the pre-processing stage, and you will get some file which with extension .i. I will show you one example. See, I'm opening one tool here that is git bash. So I have a particular command, preprocessor command. So you can see this command if I put here and if I execute it created one main.i. So from this main dot, I have a main.c file inside the core, inside the src. Here I have an here I have a main.c file somewhere. I can't see it now. Somewhere I have it. Okay. So it created a main.i. So what you can see, right, inside that main.i, it expanded everything. It expanded all the associated files, all the header files it got added. It removed all the comments. See, you can't see any unnecessary code lines here. Not code lines, unnecessary comments or text you won't be able to see here. This is what happens when you do the pre-processing on your .c file. So after pre-processing, what it does is it goes for compilation. So compilation, it has a particular command that is this one. So here you can see one E-write in pre-processing, which tells the compiler that only do pre-processing. Here you are keeping -s, which tells the compiler only do the compilation. Don't go for the entire build process. So let's do that. Oh man, copied everything. So this is the command for compiling the .i file. So I said after pre-processing, you will get a file like this. So what I am doing is now I am going for the compilation. See, compilation got succeeded. So what I will get is I will get a main.o. I have put a main.o. See, inside main.o, you can see so many things which is unresolved. That is RSS, RCC config, error handler, RCC clock config, GPIO init. These are direct names. It is not modified to its corresponding assembly code. Okay, but rest of it got compiled. So what compiler does is it check the syntaxes of your code, and it expands the code uh, without resolving the addresses. So what is mean by address resolution? That I will explain. See, here you can see one particular function is getting called by the main function, but main function don't know where this HAL in its addresses, because it is an external file somewhere inside this main.h. Okay, so address resolution is not done by the compiler. Okay, so next stage is this one, assembling. Okay, so inside assembling, what will happen? Let's see. See, inside assembly, it is converting our file to .s file, not s file, object file. Sorry, it is converting our file to object file. Got converted. So let's open that O file. Previously, yeah. See, this is .s file which created at this stage. I'm sorry, I opened a different file. After compilation, you are getting a S file, that is this one. This is in assembly language. So compiler is the one who convert high level language to assembly language. Here you can see so many assembly language instructions, but so many unresolved symbols also. It is unresolved. It is not at all converted to assembly language code. But here in main.o, so many addresses got resolved. But you can't read this main.o file just like this. It needs a different tool or something. So next one is after assembling, it will go to linker. Then it will go create one ELF file. From that ELF file, you can directly debug the code, or you can execute it, then generate it. So just I am creating that ELF file with the help of IDE only. I am not going to use any command. Just I am hitting this. So this will create one ELF file. You can see one ELF file got created. I am trying to open that also. See, this is that ELF file. So ELF file contains so many information which will help you for debugging. Also, it can be used for execution also. Why I will show you. See, this is the microcontroller, and here in properties, I am allowed to load ELF file. This is for debug purpose only. See, it executes. Then you have one .xex file. That is also done with the help of a command, but I don't have that command with me, no? But it is also done by a command. So what happens actually inside this ID, whenever you click this particular button or this particular icon, all those things, all those commands which I mentioned over here, see, I have that command making hex file out of ELF. So what happens, it execute all these commands behind this one, behind this click. So whenever you click this button, it executes all those commands and it will give you everything. You can see so many C files associated with it, right? So each and every C files will be compiled and it will be created .s file, or it will directly created to O file. So this is the behind scenes of the compilation process. Now, linker script. I am coming back to the linker script where, yeah, linker will check where to put the code. .txt section, .isr vector interrupt service routine vector. So this ISR vector also contains the reset vector. Okay, what is reset vector? Reset vector is the one which starts here. See, whenever the microcontroller boots, it starts from the reset vector. Fetches reset vector instruction from vector table. So this is what linker does. See, linker creates a vector table also. Inside that vector table, you can see the reset vector address. So everything is based on addresses. So microcontroller works based on fetching the data, which is managed by some sort of software, just like linker script, startup code, main routine. So everything plays a role in executing the code. So these are the behind scenes and tools associated with the software development on microcontroller and microprocessor. Now moving to, there is another tool called make tool and _make_file. So make tool and _make_file. I'm not going to explain this thing. That is a huge area. Like it may take 1.5 hours or 2 hours again in order to explain this make_file entire. So make_file and make_tool are associated things. Make tool is a tool, just like a compiler, assembler, linker. It is a tool which will help you to execute, all these commands which I mentioned here for pre-processing, compiling, assembling, and linking and code generation can be done with the help of this tool, make tool. A build automation tool used primarily to compile and build programs. Reads instructions from make_file. What is make_file? Make_file is a plain text file containing rules for building a project. I'm just checking whether I have an opened make_file. Yes, I have. See, here you can see it in the make_file. Make_file has the idea about where all the files are kept. Also, it has the idea what to do on files. Executable file should be _𝗏𝗏. Map file should be _𝗏𝗏map. Object copy should be whenever you are running object copy execution. See, one execution, this one, object copy. See, whenever you call object copy, it has to create a _𝗏𝗏. So it has everything. So whenever you run, whenever you type make all, it will run the main build. Main build means _𝗏𝗏 secondary output. So everything. This is a build automation tool. Take time and learn this one, make_file, and all these tools you take time and learn it. Maybe this entire session acts as a 35% of any embedded system interview, 35 or 40% of any embedded system interview. These all tools and steps are highly helpful and highly used in embedded system interview and the day-to-day work of any embedded system engineer. Now, classification of ARM architecture. So ARM is classified by different terms. ARM architecture by version. You have ARM v1 to v3, early versions not widely used now. ARM v4 introduces thumb instruction. ARM has different modes of execution. One is thumb mode, and there are so many different modes of execution are there. So next v5 added JASL support for Java acceleration for mobile computing and all those things. Then ARM v6 supports media processing. ARM v7. These area marks the revolution. Okay. Split into Cortex profile. ARM split to 3 types. ARM introduced trust zone for security. So ARM means ARM. This is also ARM architecture. But this A means application. R means real time. M means microcontroller. So most of the microcontrollers are based on ARM Cortex-M architecture. Some microcontrollers which is dedicated for smartphones, tablets, Linux-based system, they use Cortex-A architecture because they need software. They need Android, they need Linux software. So it needs a memory management unit. ARM Cortex has a memory management unit inside that, but microcontroller does not possess any memory management unit inside that. So these are the next versions. ARM v8 added 64-bit support, ARC64, improved virtualization, ARM v7 enhanced security, AI features, confidential computing. ARM v7, I think ARM v7 is there inside iPhone, latest iPhone model. They have ARM v7 core inside that. So this is the entire presentation which I have. I am saying it is completed. Now, if you wanted to ask any questions, any open discussion we have wanted to do, you can do it. We have 4 minutes. I thought I will take too much time to explain things, but it finished within time. Any questions? Hello. I'm happy that 235 people are still here after the session. Niranjana, can you just share that Google Forms link to everyone so that they can fill it? They can fill it later also, but I just wanted the feedback based on this presentation, how it went and all. So you can put your own comments using Google Forms, so that uh, it will help me to improve. Hello. Yeah. Niranjana just put the Google Form link. I am requesting everyone to fill that form so that I can have a look into it. Then I can make a progress out of it. So this is a session which is mostly theoretical. This is first time I am taking a session completely based on a theory part. Okay, lower level programming like C, but I am not that much interested in electronics designing and its implementation. Can I be able to pursue a position in embedded system? Field, can you provide the roles which align to me based on interest? Okay. Electronics designing means you don't have to be that much expert in electronic designing. Like you have to know the fundamentals of digital system, just like how basic digital steps are working. You have to know the theoretical background of things. You don't have to design the circuit. You don't have to design the internal steps of the microcontroller. You have to an expert in coding. Yeah, as you said. Adityan, can you mute? If you are not speaking, please mute. Okay, Adityan asked one question. I don't know about Verilog. Can you explain about what in short time? Simple explanation. I am going to do that. Just a second. See, this is microcontroller architecture, right? Inside that, you can see one interrupt controller. Am I audible? So inside that, you can see one interrupt controller. So it possesses some logic. It has some dedicated pins over there. Based on the pin's status, it has to tell the CPU that something is happening. So all these steps are inside the microcontroller, right? So it is a very large scale integration. So it's a VLSI device, a device manufactured by following VLSI concepts. So whenever you are designing any VLSI chip, there are different steps, like it is classified into two, front end and back end. So in front end, it comes first at design specification. What should be the design? What is the design needs? What is actually required? So that design specification would be there. After that, this design specification is converted into RTL logic, like register transfer level logic. I mean the circuit. So Verilog is the code which help you to design hardware. Verilog HDL, it is Verilog HDL, Verilog hardware description language. So Verilog will help you to realize this interrupt control unit with the help of a code called Verilog. So Verilog will help you to realize hardware inside the FPGA. So usually what we do is, like, without manufacturing the microcontroller directly, we will implement everything inside a Verilog FPGA chip with the help of. So FPGA is a prototyping chip. So we will write the code inside the FPGA chip, and we will realize the interrupt control logic there, and we will test it with the help of some test bench code, with the help of some other logic. We will test the real implementation of interrupt controller with the help of FPGA. So that is the area where Verilog comes into picture. So it helps you to realize hardware. It helps you to realize hardware inside the FPGA, so that you can have an earlier check before manufacturing actual interrupt controller inside the microcontroller. So it is a design process. It's a part of VLSI design procedure where your high-level specification is transferred into HEL. High-level specification code is transferred into realized into a circuit, a digital circuit. Okay, these are the famous protocols. Yeah. Augustine asked one question: what is the relevance of protocols like AXI4 and AMBA in the current industry? So these are the data bus protocols which is inside the processor. Like um, you have heard Intel CPUs, right? Intel and AMD CPUs. Also, we have Qualcomm. Every CPU manufacturer inside there, for carrying the data, they have different data bus architecture. One among them is AXI4, and one among them is AMDA. So these are the bus architecture which we follow in the industry in order to realize the data bus. So it's an architecture. So it has the relevance. It will be there in the future also, but maybe new architecture for the database will also come. So people are working on it, right, every day, to improve the efficiency, improve the power efficiency, execution, reducing the execution time. So it is there. AXI4 and AMBA architecture will be there in the industry for a long time. It is relevant. So this is me. I forgot to turn on audio video at the first time. So this is me. You're welcome, Maria, Christo. Welcome, Elsa. Thank you, Savio. Thank you, Avantika. Thank you, Badra. Thank you, Aslim. Thank you, Sachin. Welcome, Swati. Thank you so much, Prabhuraj. Happy to hear
Hello,
that.
sir. Am I audible?
Yes, Archana.
Yes, sir. Sorry for the delayed one. I was supposed to say the first time, but I think once we send the feedback from everyone left us.
Okay, fine, fine.
So can I do one formal thank you to you, sir?
Yeah. Please carry on.
So good evening, everyone. As we come to the close of today's enlightening session on decoding microcontroller from architecture to execution, I would like to extend our sincere appreciation on behalf of IEEE SSC Scala chapter. A special thank you to Mr. 𝗬𝗂𝗧𝗂𝗏 for guiding us through the inner working of microcontrollers with such depth, clarity, and relevance. Your ability to simplify technical concepts and connect them to practical applications made the session truly impactful. As a token of appreciation, we are happy to present a digital memento to Mr. 𝗬𝗂𝗧𝗂𝗏 in recognition of the time, effort, and expertise you shared with us today. We hope it serves as a reminder of your valued contribution to the knowledge sharing initiative. Thank you, sir.
Thank you so much, Archana. Thank you, everyone. Yeah.
A big thank you
It
to
was my
all of the participants. Yes, sir.
yeah. It was my first. It was my first experience. Yeah. Thanks so much. It is a huge crowd. More than 200 people was there online. I never attended any session like this. So yeah, it is my
We are glad to have you,
first
sir.
experience.
Also, a big thank you
Thank
to
you.
all the participants who took the time to be part of the session. Your interest and engagement are what keep these platforms alive and meaningful. We look forward to your presence in our upcoming events and our continued learning together. Thank you once again and have a wonderful evening ahead. Thank you, sir.
See you. Thank you. Good night. Bye.